Now, we're going to do the roots of complex numbers using the Moivre's theorem. So you've got numbers here, w and z are both complex numbers. So w to the power of n is equal to the complex number z. So the w will be z, taking the nth root of z. Now, by the Moivre's theorem, w can be worked out by being, it's going to be the absolute value of z, and you take the nth root of that, and then cis of theta plus 2k pi all over n. Now the proof for that you probably should have a look for can be found on page 68. We can go through it in the class if you're interested. You don't need to do the proof on the exam, but this is the format that we're going to be using. There will be n distinct roots. So what's happening in here? So obviously we're taking the nth root, so nth root of the absolute value. Now, theta is your angle. We'll get to that in a moment. There's 2k pi. So 2 pi is one complete lap around the circle. So this is just going to be the angle just going multiple laps around the circle. So every time you do one lot of 2 pi, you're back to the angle again. So we do multiple versions of that. And then we would consider values of k that go from 0, 1, 2, all the way up to n minus 1. This will make a lot more sense when we come to do an example. Let me just put one up and we'll work our way through it. So here we are. We've got z, our complex number. Z cubed is equal to 1. So what we want is to take the third root of 1. Using complex numbers, there's going to be 3 clear and distinct answers to this. First of all, writing 1 as a complex number, it's 1 in the real direction plus 0 in the imaginary direction. Of course, if you look at that on an Argand diagram, 1 in the real direction, 0 in the imaginary direction, therefore the angle that we've rotated around must be 0 degrees, 0 radians. We'll work in radians, so 0 radians. Awesome. Now, according to the Moivre's theorem, the complex number which represents the third root of unity, the third root of 1, is, first of all, it's the absolute value of the number. Well, the absolute value of this is 1, raised to the power of 1 on n, so it's going to take 1 on 3, so taking the third root of 1. And then it's going to be multiplied by cis, cos I sine, of the angle, which for us is 0, plus 2k pi over n, in this case it's 3. This will help us solve our problem, and we're going to do it for where k is equal to 0, 1 and 2. Alright, let's work through that and see what it actually gives us. So we're going to say, let's let k be equal to 0. So therefore, z1, the first of our solutions to this, will be equal to, well, the third root of 1 is just 1, so we're just going to leave that out. It's going to be cis k is equal to 0. So it's 2 times 0 times pi over 3, that comes to 0. So I've got cos 0 plus I sine 0, which equals, cos of 0 is 1, sine of 0 is 0, so this comes to 1. So if I mark it on an Argand diagram, so there we are. There is the first solution to the third root of 1. Look at the next one. Let's let k be equal to 1. Therefore, my second solution is going to be cis. K is 1, so 2 times 1 times pi over 3. So I'm going to have 2 pi on 3. So it's cos 2 pi on 3 plus I sine 2 pi on 3. Now, pi on 3, it's exactly 60 degrees. So that's 120 degrees. So we're in the second quadrant, 60 degrees off the axis. We know that cos of 60 degrees is a half, but it's in that second quadrant, so it's going to be negative a half. Plus, so sine of 60 degrees is root 3 on 2. Once again, it's in that second quadrant, so it's positive. Alright. There's my second solution. Negative a half, positive root 3 on 2i. There's Z2. Third solution. Let k be equal to 2. Therefore, the third solution will be as follows. So once again, we've just gone one lot of pi on 3 past the horizontal. So we're 60 degrees into the third quadrant. So cos of 60 is a half. We're in the third quadrant where it's negative. And then sine of 60 is root 3 on 2. Once again, the third quadrant makes it negative. So I'm going to plot that. There it is. There's the third solution. Notice each of these times, we're rotating around 2 pi on 3. And because the last one's going to rotate 2 pi on 3, that's why we only need to consider these k values here. Because if I went to k equals 3, I'm going to have the 3 there, we cancel the 3 there, I'm going to have 2 pi. Hey, I've done one complete lap back around the circle, I'm back around to there again. So because n was equal to 3 clear and distinct solutions. And that's taking the complex roots of unity.